Today we're going to be looking at integration by parts. There's a formula that you will definitely need to know, and we can post the proof for this formula if you're interested. But basically what that says is we're going to take the integral of u dv, and that's going to be equal to uv minus the integral of v du. So basically, the reason that we need to know integration by parts is because this stuff right here, this UDV, is a product. And we've undone some products when we use U substitution, and I'll show you why U substitution isn't always going to work. So the integration by parts gives us a method to undo the product rule within an integral. So let's look at an example. So let's look at the example of the integral of x times e to the x dx. So basically, this integration by parts is telling us that we need to pick out four values. We need a u, we need a dv, we need a v, and we need a du. So usually what I do is I start by listing those over on the side. So I know I'm looking for a u, and I'm going to put these in order of the variable that they're grouped with. I need a du, I need a v, and I also need a dv. So from the given integral, we should be able to pick out at least a u and a dv to start out with. And the more you do these problems, the easier it'll be to pick out what's what. Like I said, we'll kind of go through some examples and we'll see that one part isn't always u versus one part isn't always dv. But for this problem, what I'm going to do is I'm going to pick out my x to be my u, and my e to the x dx to be my dv. And I'm going to put that over here. So u is x and dv is e to the x dx. So basically what this is telling us is we're starting with some u value of x, and we need to know its derivative. That's what du is asking us to do. So the derivative of x is easy. Derivative is just 1 dx, because we're into taking the derivative with respect to x here. This part's a little bit trickier, and it can definitely get a lot trickier, kind of the more complicated functions that we deal with. But this is telling us that our derivative of some function b is e to the x dx. So what we need to know is we need to know if this is our derivative, what was our starting function? So basically to find v, we're going to be taking the integral of e to the x dx. So I'm going to write this down here just kind of as a separate step. Some of these can get a little bit complicated, especially if we're going to be dealing with some u substitution. So I'm going to say to find v, I'm basically going to be taking the integral of e to the x dx. And that's going to be what's going to go up in this blank here when I'm done with this work down here. So the integral of e to the x, this one's pretty easy. The integral of e to the x is actually just e to the x. So if my derivative function was e to the x dx, the original function that I was starting with was just e to the x. So now that we've got the four parts that we need to use the integration by parts formula, I'm going to go ahead and I'm going to take all this stuff and substitute it in, and then we will simplify. So this is telling us that we're going to start off with the product of u times v. So u times v is x times e to the x. And we're going to subtract from that the integral of v times du. So the integral of my v is e to the x. And we're multiplying that by du. Well, my du is just 1 times dx. So I'm just going to write that as dx over here. And then I need to simplify this. So I can't do anything with this x times e to the x. So I'm just going to leave that as it is. But I can take the integral of e to the x dx, which actually is exactly the same work that we just did down here to find v. So we know that the integral of e to the x dx, because we already done that work, is e to the x. But we're not done yet because we are dealing with an indefinite integral, so we do need to put the plus c at the end here. So this is telling us that the integral of x times e to the x dx is x times e to the x minus e to the x plus c. All right, so let's look at a different type of example, and you'll notice that this one looks a little bit different because it doesn't really look like there's a product going on here like we'd had in the first problem. But really, there is a product going on here. So I'm going to write out my u, my du, my v, and my dv here. And this time I'm going to set my u as the ln of x, and I'm going to set my dv as my dx, which seems kind of weird, but we'll look at that in a second. So my u is ln of x, and my dv is dx. So I'm going to start with the u. So u is equal to ln of x. What's its derivative? Well, we know that its derivative is 1 over x, and we're taking the derivative with respect to x there, so we have to put the dx. And this is basically telling us we have dv is equal to dx. Well, dx technically has a coefficient of 1 in front of it. So I'm just going to do this work down here again. This is pretty simple again, but what this is basically asking us to do to find v is we want to take the integral of 1 dx. So if this was our derivative, what was the function that we were originally starting with? Well, the integral of 1 dx is actually just x. And we can think about that as, okay, well, if we're starting with a function of x, what's the derivative of x? Well, the derivative of x is just 1 dx. So when I go to use my integration by parts formula up here, now that I've got all 4 parts here, we'll start off with the product of u times v. So u times v is ln of x times x. I'll just write the x first. So x times ln of x minus the integral of v du. So v is x, and we're multiplying that by the du value here, so times 1 over x dx. And I'm going to definitely clean this up a little bit. So I'll just pull down that x ln of x out in front, minus, technically this first x is x over 1. So we'll actually notice that this cleans up pretty nicely because the x's actually end up canceling out. So we're left taking the integral of 1 dx. And that's actually the work that we did down here at the bottom. We already know that the integral of 1 dx is just x. So this is going to be x ln of x minus the integral of 1 dx is x. And since we're dealing with an indefinite integral, we're going to put the plus c here too. So this would be our answer. All right. Let's get a little bit more complicated. So I just rewrote the formula up here so that we have it going through these 2 examples. So example 3, we want to take the integral of x to the 4th, ln of x dx. So I'll write out my u, my du, my v, and my dv. And now I need to choose. So I have to pick something for u, and I have to pick something for dv. So here's where you need to kind of play around a little bit if you're unsure. See if something works, pick something as a u, pick something as a dv, and if it doesn't work, try going back and doing it the opposite way. So I'm going to pick my u to be my ln of x. And the reason for that is taking the derivative of ln of x is pretty easy. The derivative of ln of x is just 1 over x. So that's usually kind of how I start. I think to myself, okay, well, what's an easy derivative to take? So that means that this other stuff, and I know this stuff isn't next to each other, but this other stuff that's left over is actually all dv. So dv is actually x to the 4th dx. And they don't have to be next to each other. Remember that multiplication is commutative, so we could technically write this as ln of x times x to the 4th dx if we wanted to, just so that your terms are next to each other, but you don't necessarily need to have it in that order. So I'm going to go through my process here. So my u is ln of x. We already know that its derivative is 1 over x dx. But now I need to undo this x to the 4th dx, because remember that I'm looking for its original function. So find v here. I'm looking for the integral of x to the 4th dx. So that's what's going to give me my v value, because I'm kind of working my way backwards from this x to the 4th dx. So to get the integral of x to the 4th dx, this is where that power rule comes in. So this is telling me that I'm going to increase my power by 1. and I'm going to divide by the power plus 1. So this is really going to tell me that I have x to the 5th over 5. I'm just going to rewrite this as 1/5 x to the 5th. You can keep it as x to the 5th over 5 if you want to, but this is going to make my life a little bit easier when I'm going to do my algebra in a little bit. So my v is 1/5 x to the 5th. So now I can go ahead and use my formula here. So the product of u times v is ln of x times this 1/5 x to the 5th. I'm just going to kind of rearrange terms, and I'm actually going to write that as 1/5 x to the 5th times ln of x minus the integral of v times du. So v is that 1/5 x to the 5th again. And my du this time is 1 over x dx. So I definitely want to clean this stuff up. That's inside the integral right now. So I'm just going to bring down this 1/5 x to the 5th ln of x minus, and I'm noticing that I have a 1/5 here. I'm actually going to pull it out front. And that's going to be the integral of, I'm going to be left with x to the 5th over x dx. So again, I can still kind of clean that up a little bit. Focus in here a little bit better. And I'm noticing that I've got an x that can cancel the top and the bottom. So 1/5 x to the 5th ln of x minus 1/5 times the integral x to the 5th divided by x gives me x to the 4th dx. And oh wait, look at that. We already did that work down here. So we know that that integral is going to be 1/5 x to the 5th. So bring down this 1/5 x to the 5th ln of x minus 1/5 times, and now I'm going to put that stuff that we know is the integral of x to the 4th dx, which is 1/5 x to the 5th. And again, I'm dealing with an indefinite integral here, so I'm just going to plop in that plus c right at the moment, and now I'm just going to clean this up a little bit. So 1/5 x to the 5th ln of x minus 1/5 times 1/5 is 1 over 25 x to the 5th plus c. And you can definitely leave this like this in this form if you wanted to. Sometimes you'll see that there's a GCF that could be factored out. If that's the case, then you might see it written a little bit differently. So the GCF here would be 1/5 x to the 5th. So you might see that written as times the quantity of ln of x minus 1/5, and then plus c out here. All right, let's go and look at an example with what we were doing a couple weeks ago with the inverse trig. So we'll throw some of that in here. So our example 4 is to take the integral of arctan x dx. Remember that arctan is just a different way of writing that tan with the kind of like -1 exponent there of x dx. So if you like this way a little bit better, you can always rewrite that. So again, I'm looking for 4 values here. I'm looking for a u, I'm looking for a du, a v, and a dv. And this one's pretty straightforward in terms of what you're going to pick for what, because you should know about this derivative. We talked about derivative of inverse tangent, inverse sine, inverse cosine functions. So that's what I'm going to set as u, because I know what its derivative is. So that means that this dx part is actually my dv. So my du part is going to be the derivative of the inverse tan, which I know is 1 over 1 plus x squared dx. And this dx that we set as our dv, remember we did this on the last example before. So to find v, we're looking for the integral of, technically that's a 1 dx. So that original function that would have gotten us this 1 dx would have been an x. So our v is an x. So let's go ahead and use our formula here. So product of u times v. So the inverse of tan times x, I'll write that as x times the inverse tan, minus the integral of v times du. So v is x times du is 1 over 1 plus x squared, and then dx here. All right, so there's a couple different ways that we can approach this problem. I'm going to clean up the stuff that's on the inside of the integral right at the moment, and I'm going to write that as one fraction. So that's going to give me, oops, that should be a minus, the integral of x over 1 plus x squared dx. So in a problem like this, and we'll kind of go over some methods over the next couple days, we actually know how to take the antiderivative of something like this by using u substitution. So I'm going to do another step of work down here at the bottom of my paper. So I'm looking for the integral of x times 1 plus x squared dx. So what I'm noticing is I could set u equal to, and I know that's kind of like a different u than we're dealing with up here. We'll kind of go back and substitute in afterwards. Just looking at this, thinking about it as kind of its own separate problem, u I could set as 1 plus x squared. And again, I'm using u substitution here. So I'm going to say du is 2x dx. And when I solve for dx, that's going to give me du over 2x. So if I go to use u substitution and say I'm going to leave my numerator of x the same, but I'm going to put that u in for that 1 plus x squared, and then dx we know is du over 2x, I'm noticing that my x's are going to cancel out up here. So what I'm left with is 1 over 2u du, which I could factor out that 1/2, which leaves me with the integral of 1 over u. Well, we know the integral of 1 over u is 1/2 times the ln of the absolute value of u. And now I know that I can go back and plug in the u value here. So ln of 1 plus x squared. So this is actually this piece right here. So I'm going to go and I'm going to pull down that x times the tangent inverse minus, and the integral of x over 1 plus x squared is actually 1/2 ln of 1 plus x squared. And then I'm going to put a plus c here. So that would be the integral of the inverse tan function. So some of these you might have to do a little bit more work on. Some of them might require some more steps that you might have to solve separately, like this. If you solve this separately, I would maybe suggest kind of doing it somewhere else on your paper so that you're not confused about like kind of this stuff going on and then getting that mixed up with the stuff going on and then going back and making sure that you're substituting it back at the end. All right, so what happens when we are given a definite integral? So the last couple of examples were just indefinite. So what happens when we have kind of some limits here to work with? Well, the formula is going to look pretty similar, but the difference is that we're just going to be evaluating the pieces separately. And we're going to be doing this by hand using the FTC. But the process is still going to start off the same. So I'm still looking for a U, a DU, a V, and a DV here. So again, kind of with more practice, you should be able to kind of pick out what you're going to kind of set as U and DV. I'm going to set my U as an X, which means that my DV is going to be this cosine of X dx. So my du is pretty easy here. My du is just the derivative of x, which is 1 dx. And to find v, this is really telling me to take this cosine of x dx and go backwards because this is the derivative of a function. I want to know what I'm starting with. So the integral of cosine of x dx, here's our trig rules coming into play here. That is going to be sine of x. Because if I start with a function of sine of x and I take its derivative, well, the derivative of sine is cosine. So that's kind of why this relationship works here. So now that I know my pieces, I'm going to go ahead and use my formula that we were using in the last couple of examples, but the difference is that I'm going to put some kind of bounds or some pieces that I need to evaluate on now. So my first part is the product of u times v, so x times sine of x. And I'm going to put that kind of in brackets, and I'm going to put the limits here. So I'm evaluating that product from 0 to pi. And then I'm subtracting out the integral from 0 to pi of v times du. So sine of x is the v, and the du is just 1 dx. So I'm just going to write that as dx. And I'm just going to kind of pull this stuff down for a second. Oops, that's x sine x from 0 to pi. And then I want to take the antiderivative of sine. Well, here's another trig rule here. What is the antiderivative of sine? That would be negative cosine. And that piece I'm also going to be evaluating from 0 to pi. And there are a couple of algebra steps that you can do here. It's up to you of what you want to do in terms of like this double negative here. That is technically a negative one that you could pull out to make a plus here. I'm going to evaluate the way it is, but it is up to you kind of what you want to do here. So I'm going to do this first piece of x sine of x evaluated from 0 to pi. So my FTC tells me to take pi times sine of pi, and I'm going to subtract out evaluating at 0. So 0 times sine of 0. So that's this piece here written out with the FTC. So pi times sine of pi minus 0 times sine of 0. Then I'm going to subtract out, and I'm just going to leave this the way it is. I'm not actually going to go and pull out that -1, but it is up to you of what you want to do. So I'm going to evaluate negative cosine of pi minus negative cosine of 0. Just again, be careful about the algebra. If you do keep that negative in like I did, just be careful about your minus signs here. And now it's time to actually evaluate. So pi times sine of pi is actually just 0, minus 0, sine of 0 is still just 0. So this whole thing in the first set of brackets here actually just ends up being 0, but I'll simplify that in the next step. Minus, here we have cosine of pi. Well, cosine of pi is -1, but I'm just dropping down the minus that's already in front of that there. So I have to pull down that minus. And then I'm going to plug in -1 for cosine of pi. I'm going to make this into a plus because that double negative becomes a positive. And then I'm evaluating cosine of 0, which is just +1. So here, this just ends up being a 0. I'll put down that minus in between. This is actually going to become this double negative here. It's going to become a +1. So that becomes 1 plus 1. So this actually just ends up being -2. And that would be our answer. So that's telling us that this whole integral, so the integral from 0 to pi of x cosine of x dx, gives us an answer of -2. So it's your turn to do some practice problems. Let us know if you have any questions.